Hey, what's up, sports fans? Yet another lesson coming at you. This is now 11.4, measuring electrical resistance. Notice how I've crossed out this YouTube link. I tried it and it doesn't work, so we don't have a YouTube video for this section, but I'm sure that you could find some if you have a look. If you find one that you think is very helpful, then let me know and we can post it up on the thing. But I'm going to go through this. I most likely will have a supplementary video for this, as well as the other section, just to have some more tutorials to show you how to do these in more detail. But I figure I'll go through these now because some of you might just be able to go through and sort of get it, and you can go ahead. And then if people have trouble, then I can make more videos, maybe answering some homework questions and things to give you a bit of practice with these, because this lesson here in particular is now the math part, right? We're going to be doing lots of math, nothing super complicated, but can be tricky, especially tricky for me to try and explain, maybe not being done in real time. So I'm going to try my best. We'll do some stuff together. Hopefully this will be helpful and will kind of get you there, and I can make some supplementary stuff too, sort of drive the stuff home. Okay, so let's just go through this, and we will, and then and then we can discuss kind of after. All right, so three things to measure resistance. We need current and voltage and resistance, right? So these three things are all related, and we're going to figure out how, right? So just a refresher. Current symbol. This is an I. I know that you can't really tell. This is our story of my life. Chlorine, symbol for chlorine is uppercase C, lowercase l, but it looks like CI, right? So remember that current is an I, and that is just because of this font, right? If I make it like Times New Roman, though, right? Then if I change the font, notice how all of a sudden it has little, these are called serifs, actually. It has little things, so you can see it's not. Okay, so electric current is symbol I. The rate of movement of electric charge. Potential difference or voltage is the difference between the electric potential energy per unit of charge at 2 points in the circuit, right? Electrical resistance, the property of a substance that hinders electric current and converts electrical energy into other forms of energy. How do we measure each of these? We measure current with units of amps or amperes, right? Either is fine. Amps is just a short form instead of having to say the full name of amperes. And we use an ammeter to do that, right? The potential difference or the voltage is measured in volts, so that's nice and easy, V and V. And we use a voltmeter for that, so easy to remember. Now, electrical resistance is measured in ohms, right? Named after George Ohm, and we're going to talk about his law now. And it has this symbol here, which is actually the Greek letter omega. It's an uppercase Greek letter. You see this, you probably see this in church on the big candle. Every church that you go into will have a very, very tall white candle. It's usually, I think, probably next to where the priest gets up to give his homily, or where people get up to talk at the lector. It'll be near there, and so you should see the symbol on it, right? Because alpha and omega. So that's a little tidbit. Just nice thing about working in a Catholic school is we can talk about that. I guess we can talk about it at any school, but just a little thing there. See if you know why there's the omega on it. There's also another letter that will be on that candle. Well, it might technically three, or there's two other symbols that might be on that level, that on that candle. Also, the other symbol would be an alpha. So alpha and omega. So if you want a little fun thing, you can pause the video. So think about why and pause the video. Okay, yeah, because Jesus said he was the Alpha and the Omega, right? And that's Alpha, the first letter of the Greek alphabet, Omega, the last letter of the Greek alphabet. So I'm the beginning and the end, right? So that's what he said. So, anyways, interesting. We measure electrical resistance with an ohm meter, and then the symbol for resistance is just an R, okay? This is an example. This is like a picture of what a resistor looks like in actual circuits. If you have looked at any circuits before, if you have like an old piece of electronics that you're throwing out anyways, try unscrew it, open it up, and have a look at the circuit board, because you'll see these little resistors in there, right? They're in everything, right? You need them in everything, so these are resistors. The filament on an incandescent light bulb is a resistor, because basically everything you plug into a circuit will slow down the current to some extent, right? But you have these things that are specifically only resistors. They're devices used to control the current and potential difference through a component in a circuit by a specific amount, because certain parts of circuits you need a certain amount of energy to do some things, right? But then you either have to like sort of, oh, I need lots of current here, I need a little bit of current there. So you put these resistors through in order to regulate the current through your thing, through your circuit, or else you might have shortages, right? You might have too much current, which might damage some of your electric components, which you don't want, obviously. Okay, let's talk about Ohm's law. George Ohm is a German physicist. He measured the current and potential difference in circuits that contain metal wires. He found that for most wires, the ratio, so that's just like dividing two numbers, if you divided the potential difference by the current, or just compare these two numbers together, he found out that that ratio was always a constant, right? It didn't really matter what it was. That if he looked at the potential difference across a wire, given a particular current, that it would end up being this constant ratio, right? And so that constant he called the resistance, and he defined it, above, like we said, the amount that the current's being slowed down. But mathematically, it's the ratio of the potential difference across a load to the amount of current passing through the load. So if we divide voltage by current, that will tell us the resistance, right, of whatever in the circuit, right? If it's the wire, if it's a load, light bulb, whatever, right? It'll tell us how much resistance that has. So this nice little simple 3-variable equation, very, very similar to our density equation from way back, right? Density is equal to mass divided by volume, and you can use the exact same technique to solve these types of questions now. But we just have obviously different quantities that we're using, okay? And then he called this Ohm's law, because this relationship is referred to as Ohm's law. And instead of you doing the ratio, sometimes you do it as the product of current multiplied by the resistance to give you the voltage of something, okay? Showing us the relationship. And to get from here to here, you just rearrange this equation, which we have done before, okay? So what this is saying, though, is that the current and resistance are inversely proportional. So if you look at resistance here and then current is on the denominator. So as current increases, that will actually decrease the value for resistance. And then the opposite is true. As resistance goes up, the current will decrease, right? Which makes sense. The more resistance there is in something, the less current. And the more current we have, it means there's less resistance. So just pointing out that relationship between the two of them, whereas resistance and voltage are directly proportional, meaning that as resistance goes up, the voltage also goes up. So the larger the resistance in a circuit, the smaller current, right? Just like what we said. So resistor acts to reduce the current moving through a circuit, okay? Units of resistance. So if we look at these things like the units, it's a volt per ampere, and we just call these things an ohm, right? Remember in our previous example, we were saying how much current passes per unit of time, and we called that an ampere, right? And then we said, okay, how much energy per unit charge? We called that a volt. So basically all three of these units that we're using for these are a combination of two other units, right? So we're basically, just to make things simple, instead of always having to use this V and A, we use this ohm, right? And then they picked the Greek letter omega, I think because it sort of sounds like the beginning of his name, I think, right? So omega, ohm, is probably why they picked it. So just pointing out that like this is not like our standard alphabet. It's a Greek letter, so that's why it looks funny, which you might not have seen before. But we use lots of Greek letters in science, so get used to it. So you'll learn the whole alphabet eventually if you take science into university. So according to Ohm's law, if the potential difference of 1 volt across an electrical load causes 1 amp of current to flow through it, the resistance of the load is 1 ohm. That's just what the definition of an ohm is, which we know. And let's talk about how to solve problems. So we rearrange the formula of Ohm's law to allow us to find either the current or potential difference. So here's that nifty triangle. Remember, if you really want to do more science and do more math, I would strongly recommend not using these triangles. I would recommend being able to rearrange the equation algebraically in your head. So start with one form of the equation that you can remember, and then if you know some algebra, then you can rearrange to get the other forms. But here they are, 3 different forms with a different variable isolated, right? And we can use our grasp method again. So let's take a look at a sample problem. I know it's not as good because I won't be hand writing it, but I will be typing it out as we go to to help with that. So feel free to make use of pausing the video. I would recommend that at this point, why don't you grab like a sheet of paper, a pencil, and a calculator, and you can go through this with me and pause as you go. So pause now and get those things. Okay, good. So you hopefully have some stuff, and I would recommend you go through it. So let's read through it together, and then you can try it on your own, and then wait for me and then you can wait for me to do it if you get stuck. Okay, so it says a technician is checking the circuits on a vehicle. Okay, it doesn't really matter. The technician measures the current entering a component as this many amps, right? 0.47 amps. Potential difference across the component is 12 volts. What is the resistance? Use graphs to solve the problem. Okay. So reading through the question, there's some info that we don't really need. We're only really interested in these numbers. So what does the G stand for in the graph? Well, it stands for the given. And what are we given? We are given the current I of one component, which is 0.47. And then I'm going to just do a couple spaces. And then we're also given the voltage, which is equal to 12 volts. Okay, so that was our given. R, what does the R stand for? R was our required. Well, what are we looking for in this? Well, we're looking for the resistance, right? Because it says, what is the resistance? Then the A, analysis, I believe, right? So what we have to figure out is there an equation that we can use that uses current and voltage to give us the resistance? So we look up here, we see that, well, hey, look, resistance is equal to voltage divided by current. So if I use that formula, then I should be able to find my resistance, okay? So then we go to S, which I think what solution, solve, I can't remember exactly what it's called, where we just basically plug in R is equal to, and then our 12 volts divided by 0.47 amps. Important to include the units there, and then I will need another little line, but I'll just do an equal sign, maybe line it up so that you know where it's coming from. And then I do this. I don't know what that is off the top of my head, so I get my calculator. I think it's going to be some, is it something even? No. 12 divided by 0.47 gives us 25.53, and then I'll round that, 532. We don't really need that many. How many decimals do you need? A good rule of thumb is if you have an answer that gives you a decimal, if you have something with a decimal in it, just use that number of decimal places. So we have a 12, which with no decimals after, and we have this guy with 2. So we may as well just keep these 2, right? So I'll write out my full answer. Oh, and don't forget to include our units to show you how to get to that symbol. So in Microsoft Word, if you go to the Insert tab, the advanced symbol is on the far right. My computer is slow. It'll take a little while to load. And then you have a whole bunch of symbols up here. If you take a look, you have, this is the Greek alphabet up here, right? And then omega is way at the end over there. And then you just hit insert and then close, and then boom, I have my little ohm symbol, which is kind of nice. But I'm going to round that. So notice that I've put my big kind of answer, and then I'm going to put my rounded answer, which will be my final one, right? So then I'll have 25.5. And how do I round that? Do I round it up to a 4, or do I leave it as a 3? I leave it as a 3, right? Because this 2 is less than 5, so then I leave my 3 as is. And then I will reuse my symbol for ohm. This is just a good practice. It helps your teacher sort of see all the processes you make, right? So by writing everything out individual steps like this, it's really easy for me to see where you are making mistakes, right? It also can help slow things down for you so you're not doing things too fast, because if you try and do too much in your head, then it's easy to get confused and write down the wrong answer, even, right? And because you're going so fast, you might not be thinking about it. So writing it all step by step like this lets me see, and then let's say that if by accident you rounded the wrong thing, right? Then I can say, oh, it's just a rounding error. It's not a big deal. You know what I mean? It lets me sort of see where you're making these mistakes. So I like this showing like, okay, here's what I'm going to do. I'm going to divide these two numbers. Then I have the answer with the division, and then I have my final rounded, like neat final answer at the very end down here, so that I can see, okay, they did the division properly, and then they know how to round these numbers properly. And then P, which I think is paraphrase, sorry, is it not paraphrase? Or I forget what it is, but then you can just say something like, therefore, the resistance of the component is 25.53 ohms. And then that's it. Okay? Hopefully that worked out okay for you. Why don't we try doing this one together as well, which might help, and then we'll just finish through this stuff on our own. So an electric toy has a resistance of 120 ohms and requires a current of 0.05 amps to work properly. How many 1.5 volt cells does the toy require? Use graphs to solve this problem. Ooh, a pretty tricky one, right? Because there's going to be an extra thing to do here. So why don't you try and pause the video, take a stab at it if you can, and then I will go through it. All right, so what are we given in this question? What is our G? We are given the resistance of the toy, which is actually 120 ohms. Oh, it looks like I am using a different font for some reason, which is 120 ohms. And what else? And then there's a couple spaces here. And we also know the current, right? The current is equal to 0.050 amps. Okay. And we know the current for the electric toy, right? Now, this is the interesting thing here. What are we looking for, right? What are we required to find? The required is how many 1.5 volt cells does the toy require? So it's how many cells is what we're looking for, right? Which is a little bit strange. So what else do you think we're going to be looking for here, though? Because if we have the resistance and the current, we're probably going to need to know what the voltage is, right? Oh, I'm sorry. The other thing that we are also given is we know the that the voltage for an individual cell is 1.5 volts, right? For the battery, right? To go in this, right? So basically, there's an electric toy. It has this much resistance and it needs this much current. So how many cells does it require? So basically, we're trying to figure out like what kind of battery do we put into this, right? So what we will probably need to find here is the total what's it called? The total voltage, right? We'll need to find the total voltage going through this, but ultimately the number of cells is the important question. That's what we're looking for. That's what the question is asking us, okay? So that's an important little twist here, right? We give you something straightforward, but then throw in a little curveball. So please make sure that you answer it correctly, right? If you just told me the final voltage, that's only halfway. Okay, so how are we going to do this? So how are we going to analyze this, this question? Or what analysis are we going to go through? Well, I think that it's safe to say that we're going to need to find a total voltage, right? Because we can't do much without that. So how do we find the total voltage of the whole thing? Well, that's going to be of the toy, basically, or the voltage that T could stand for the toy. We take a look up at our equations. Which of these equations? Aha, V equals I times R. So equals I times R, current times resistance, right? That will tell us the voltage of the toy, right, total. But then there's another question. What other equation or what other kind of relationship are we going to use to figure out how many cells we have kind of at the end, right, for our final answer? Well, like we talked about before, the individual cells make up 1.5 volts, right? So to find the number of those cells, we just have to do a division. We know that the total voltage will be equal to the voltage of the cell, of the individual cells, multiplied by the number of cells, right? We know that relationship. So if I multiply 1.5 by how many cells there are, that will tell us the total voltage, right? But we're going to have to go about this a different way because I can actually find the total voltage from this current and resistance, and I'm looking for the number of cells, right? So I have to rearrange this equation so that the number of cells will be equal to the total voltage divided by the voltage of the individual cells, right? which, if I just do another thing real quick to plug in some numbers, is going to be the same thing as whatever the total voltage is, which we haven't found out yet, divided by 1.5 volts. So we can use this equation here to find our total voltage, and then we just divide that by 1.5, and then we can find how many cells that will give us the number. Okay, analysis, grasp. It's time for the solution. So let's do some of the math, okay? Let's take this equation here. Just going to copy and paste real fast. And then plug in some of the values. The current is 0.050 amps. We're going to multiply that by 120 ohms. Include these units. So again, 0.05. What is that? That's like half a tenth, 120. Is it? It's not half, 60, 30, I think. Is that it? Oh, it's 6. 6, and what units do we have? Volts, right? So always important to remember the units of the final answer, because that we're looking for a voltage, so our answer will be in volts, right? 0.05, yeah, good. How many decimal places? We get a nice even 6. So what I'm going to do, let's just leave it at 6 to be honest, because we can put 6.00, it doesn't really matter. So I'm not too picky. So let's just use a nice even number of 6 volts, but we're not done, right? That's not the full solution. So we found the total voltage. We have to find the number of cells, though. So the number of cells is going to be equal to this thing here, right? Just to reiterate it, oops, more space, it's going to be equal to that. So therefore, we found that the total voltage is 6 divided by 1.5. And that gives us what? Gives us a nice even 4. Notice that we're dividing by the same units here, right? So if you're like, well, sir, what units should I have? Well, a number of something doesn't have any units, right? I have 5 apples. I don't have any units for that. So it works out nicely because the volts on top and volts on the bottom will cancel each other out, leaving us with a dimensionless, a unitless answer, which is just 4 for our solution. And then we will paraphrase or paragraph. I'm really sorry, I can't even remember. I usually use GRASP, and I think it's solution in GRASP. GRASP, I can't remember. I don't care what it is, as long as you put something in for it, then that is fine. The toy needs 4 cells, right? Or it needs 4 1.5 volt cells. And I'm going to write the number out. Putting numbers next to each other like that is kind of confusing, especially when we've been doing math, so I'm going to put 4 1.5 volt cells. And that's it. Okay, hopefully that's helpful, and hopefully that's good, and hopefully you are doing okay. This is difficult to teach this way because I don't get any feedback. I just sort of have to keep going, and I don't know when to stop. So you are sort of doing a lot of the heavy lifting here. Pause the video as much as possible and rewind if you need to. Okay, let's just go through this quick. We don't have to talk about graphing it too much. To find the value for resistance, we can add cells in series, measure the difference for each load, and measure the change in current through the load. You can then graph the linear relationship of the potential difference in the current and find the slope of the line to find the resistance, okay? It seems really confusing, I know, but we have like, here's a battery. We can put an ammeter and a voltmeter in something. If we don't know the resistance of something, we just connect these meters. If we don't have our ohm meter for whatever reason, we can measure the voltage and current, and then we can actually plot those on a graph to find the resistance, okay? For the whole thing. If we want like an individual point, we can just do the calculation, but if we want to sort of look at a different number of values and sort of look at the trend overall, then we can make a graph. So potential difference is measured using the voltmeter. We know how current is measured. Anyways, here's a little bit of math. Maybe you're doing it now, maybe you've already done it, I don't know. But just to reiterate how to find the slope of a line, remember we have a y and an x axis. We have a bunch of points. We have 3 points, right? And so in order to find the slope of the line, which gives you sort of like an average, if that makes sense, because we are plotting, what is it, current versus potential difference. And if we look at, it's just looking for patterns between two variables, right? Anyways, so how do you find that? You take you assign 0.2 and 0.1, doesn't really matter where. 1 point on somewhere, the other point somewhere else, and then we take their x and y values, right? And then to find the slope, remember that it's y2 minus y1 over x2 minus x1. So basically the y values from 0.2 and 0.1 go at the top, and we subtract them, and then the x values for those 2 points go on the bottom. We call the y values the rise because it kind of goes up and down, and then the x values are the run because it's like you're running on a flat surface. And then we just divide those two, right? We do the subtraction, get the number, and then divide them. And then what that tells us, the slope of a line, if we plot it current versus potential difference, will tell us the resistance. Current versus potential. If we plot those two things together and we find the slope of that line, the slope of the line will be the resistance for the circuit, which is pretty interesting, right? And that's why it's called Ohm's laws. This is what George Ohm did. He plotted these things on a graph, and that's what he found. And so you notice that the slope of the line is constant, right? It's the same for every point on the line. And it tells you how steep the line is, right? So it tells you basically how much the y value increases with respect to the x value, right? So in this case, how much the potential difference goes up based off of the current, right? Which we mentioned before that's a fixed ratio, okay? So voltage goes on the y-axis, current goes on the x, and we find the things, and we can find the slope that way. Just a little math reiteration. Okay, this is more conceptual. Now I gotta make this go on another page so I can see it. Factors that affect resistance of wires. So this is non-numerical, which is maybe nice for some of you. Ohm discovered the resistance of wires had 4 important factors. The factors that affect the resistance of a thing, that lead to the resistance, are the type of material, the temperature of the wire, the length of the wire, and how fat it is, basically. The cross-sectional area is sort of how thick the wire is. So the material choice, for example, it depends on the metal or whatever you use, right? If it's, we said some metals are better conductors than others. So silver has very little resistance, but it's expensive, so we use copper. So copper actually, so silver and copper have different resistances, right? Silver has a lower resistance just naturally than the copper does, right? That's just built into the material itself. You can't change that in any way. That just comes from the chemical property. Did we say that conductivity was chemical? I think it's a physical property. Oh dear, I can't remember now. But we did mention about physical chemical property, but it comes from the property of the substance itself. Whereas the temperature is something that you obviously can change. So if the temperature goes up, the resistance goes up as well, right? So if the resistance increases, it means that the conductivity isn't very good, right? It becomes a worse conductor. So if you want something to conduct better, a metal to conduct better, then you can try and decrease the temperature, right, to increase the amount of conductivity. So temperature going up means resistance goes up as well. The length of the wire, how long the wire itself is, can affect the resistance as well, meaning that wires that are longer will actually have more resistance than wires that are shorter, right? If the wire doubles in length, it doubles in resistance. So there's a direct relationship there, which makes sense, right? The longer the wire, sort of the more distance electrons have to move through. If you picture like a hallway with like students, you know, when the bell rings, trigger warning for large crowds if you're not ready for that. But hopefully it's okay. Just picture a hallway, a bunch of kids in it, you know, walk through the hallway. The longer the hallway is, the sort of, it'll take you more time to get through. Whereas like if the hallway is kind of short, then obviously it'll take you a bit less, if that makes sense. So longer wire means more resistance, shorter wire means less. And then how thick the wire is will change the resistance as well, because if the wire is bigger, there's less resistance, which again makes sense. Picture that same hallway. If it's a really narrow hallway, then I have to push through people. You know, it takes me a long time, lots of resistance. If the hallway is nice and wide, I can get around quite easily. I can just avoid people. You know what I mean? Like there's my physical distancing. I can do that in the cross-sectional area there. Okay. So 4 factors that affect resistance are these these 4 here. Okay, let's talk about superconductors quick, because they're actually quite interesting. A superconductor is a material through which electric charge can flow with basically no resistance. So our regular conductors we talked about are just our typical metals, and we also mentioned things that were called semiconductors, right? There are these another class that are called superconductors, and they're special materials, and they conduct electricity with almost no resistance, which is great, right? It seems like a great idea, but the problem is that you usually have to cool them down quite significantly. So you can make a superconductor, so you can make it in a lab, but it won't actually conduct anything until you cool a lot of these down with liquid nitrogen. So you can see examples of that, of these materials becoming magnetic as they get cooled with liquid nitrogen. You can find those videos on YouTube if you just look up superconductor cold. I'm sure something will come up. But that's the problem. We can't make wires out of these things because you have to cool them down to the liquid nitrogen temperature, which is very, very, very cold, right? You can't do that. You can't wire a city with all that. You can't pump that much liquid nitrogen through it because the energy that would be required to keep it at that low temperature would be crazy, right? So it's just too much. So it's not viable to make, let's say, wires out of superconductor material. So increases as temperature, however, wire would not transform electrical energy into heat, right? So they're very efficient, these superconductors, and you can see some examples of them in those, not for their, well, for their conducting ability, but in bullet trains, those really, really fast trains that are in like Japan and stuff, they use magnets so like it's kind of similar. They use magnets for the train to go, so the train isn't actually touching anything, and it's a similar thing. So if there's no friction on the train, then it can just go sort of like it can go a lot faster than usual, and it won't get slowed down, right? And you use these like kind of superconducting magnets is the idea to do it. At least I think, unless I could be way wrong on this. I think I learned this somewhere. I can't exactly remember, but look that up and correct me if I am wrong. But that's what a superconductor is. It basically conducts stuff with no resistance, and there's still lots of research to be done. And then another thing is called a non-ohmic conductor. So it's something that doesn't follow Ohm's law. It's a conductor of some kind that doesn't follow this direct relationship, right? So if we plot the current versus potential, what's called an ohmic load, a traditional ohmic device will have a linear relationship, right, like we talked about, whereas some other device that doesn't obey this law will have a nonlinear relationship there. So we call those non-ohmic, right? Basically just kind of because the world is imperfect, not all of our materials behave the way that we think that they will. So sometimes we get curveballs for them, but we can, and so we might have to compensate a little bit, but ultimately it's not like that big a deal. So just want to talk about that there are some things out there that do conduct electricity, but in a non-ohmic way. So not everything is the same is basically the takeaway. All right, heavy lesson, very difficult. Hopefully you're doing okay. Please let me know if you're not, okay?